Reservations in two-way slabs by means of yield lines. This video deals with cases 26 to 30. It's about a concrete slab where the two opposite longest sides of the slab is hooked and the short side in opposite are simply supported. This is case 27. It's about a corner hole following the yield line. We start now with case 27. We look at the different geometric parameters. And we know that because it's a two-way slab, that B, the distance B, must be between A and 2A. The reservation is in the corner, so it follows the yield line. So it means that the slope must be equal. The slope d2 over d1 must be equal to s1 over s4. This is s1 and this is s4. So just the tip of this reservation follows the slope of the yield line. Top left corner, so it means that d3 is 0 and d4 is also 0. And it's only cutting one yield line there, so it stops here. It means that d1 can never be bigger than 4. So it means this from there to there. We can now we have substitute the different variables in it. So these are the conditions of a case 27 hole. Visualizing it can be shown. You will see it as follows. It's just square, or it's not square, but a reservation following the yield line at an angle of 60 degrees. We will now calculate the energy, the work done by the external forces. We know that it is a summation of triangles, the effect of triangles and squares and rectangles. For the rectangles, sorry, this is the orange part. It is of course A times this, which is B minus S1 minus S3, and the mean deflection is A over 2, delta over 2, because it's a rectangular. Then we add up all the triangles, and we got from this side A times S3, on the other side 2, A times S1, but there's a reservation in it, and we have to subtract it. First portion is D1 times D2 divided by 2, which is this surface, and the maximum deflection is D1 over S4, because it's rotating about this axis. So that's this portion. And we subtract also the other side, which is rotating about this axis. So it's d2 times d1 divided by 2. And the maximum deflection there is d2 over s1. We know that s1 and s3 is this value from the geometry. We work with unitless parameters. And then you can substitute the different values, and you find this as a formulation. The work done by the internal forces is the bending moment projected to this axis of rotation, which is m times the b minus d2, and the angle of rotation is delta over s4. Then we got this line. It's also the same. It's in fact, if you project it to this axis, it's from there to there. You got b minus d2 divided by s4. So that's why there's a 2. At the bottom, we got b projected on this axis. So we got m times b divided by 2. And for this negative yield line, it's also b divided by s2. On the other side, we have a times divided by s3. And on this side, we have a minus d1. It's only this portion from there to there. So it is m times a minus d1 divided by the rotation, which is delta over S1. Then we have this, substituting the different parameters, and we arrive at the equation. By putting d equal to E, we get m, and we can put we have now m as a function of alpha, which is b over a, and alpha 1, which is b1 over a. So d2 is fixed because of this following the yield line. So we have this relationship. Now let's look at an example. We have a concrete slab of 5 by 5 meters, and we want to make a reservation into the slab of 1.5 by 0.9 meters. This is a slab with a depth of 160 millimeters, concrete cover 30, floor finish of 2, and a mobile load of 10 kilonewtons per square meter. What is the needed reinforcement in this slab? We calculate the load in ULS, and it's 1.35 times the permanent load plus 1.5 times the mobile load gives you 23.1 kilonewton per square meter. Different parameters. We check if it's case 27, so d1 over d2 over d1 must be 1 over the tangents of 60 degrees, so it's okay. We use the formula of the previous slides, and the maximum bending moment is 17.22 kilonewton meter per meter. We convert that into reinforcement, and therefore we calculate the mean lever arm, which is 122 millimeters. The needed reinforcement is then 1.1 times the maximum bending moment divided by the lever arm and the yield strength of the reinforcement. And it gives us 400 square millimeter per meter, which is 8 times diameter 8, and it is in X direction, Y direction, top and bottom. Then we can have another example where there is an existing slab. We do not know what reinforcement is in there, nor the concrete quality, nor the original load of the slab. So this slab is, you know, that it's reinforced in 2 directions, and we wonder if it's okay if we make a reservation in the corner of 1 by 0.6 meters. To tackle this problem, we look at the maximum bending moment without the reservation. So we assume that the slab was properly designed, and we divide M0 by the ultimate load because we do not know the load. So what's left is something that we can calculate, and it's 0.676. Then we calculate the maximum bending moment with the reservation. We divide also by the ultimate limit load, and we have 0.727 meter per meter. This means that the bearing capacity is 93%. So we lose 7% of the bearing capacity by making a hole of 1 by 0.6 meters in the top left corner of this type of slab. That's why you should always avoid to make reservations in the corner of the slab. Bearing capacity, we defined it as 100 times maximum bending moment without the hole divided by the maximum bending moment with the hole. In the formulation, it looks like this. We work with unitless parameters, and the case 27 type of hole or reservations, they must have the following restrictions. This is following the yield line. And then we can substitute this in the formula of the bearing capacity. Substitute M0 and M, and we have this formulation. This formulation can be put into a graph, alpha 1 on the x-axis, going from 0 to 0.5 times the smallest size of the concrete slab. On the y-axis, the bearing capacity. And we do that for alpha between 1, a square slab, to 2, and that's the range of the one-way slab, and for the different possible parameters of alpha 1. The first thing we notice is that the bearing capacity is always decreasing. Always. So making case 27 reservation will lead also every time to a loss in bearing capacity. And this loss is between the black line and the red line. The maximum loss can go to 10% for a square slab, and it happens with size of the reservation of 0.385 times A. So it looks a little bit like this, where the reservation is in the corner. This leads you to the maximum loss of 10% in bearing capacity. When you have the slab with alpha 1.5, then the maximum bearing capacity is at alpha 1 equals to 0.435. Or for the alpha equals to 2, we have alpha 1 equal to 0.46, which is giving you the maximum loss in bearing capacity. So as a summary, we can say that a reservation of type 27 following the yield line of a rectangular concrete slab leads to a loss of bearing capacity of maximum 10%. But we should add that there is always a loss of bearing capacity when you make a reservation in the corner of the slab.